An example would be this M-trop I defined before. There's also an example of tropical curves with piecewise linear functions, I think. And of course, the picard that we're going to define should be such a thing as well. But we'll see that later on, I think. I hope. But, I mean, from other points of view, as I said before, as I said at the end of Rose's talk, actually, this is not really a nice thing to look at. I think, at least. I don't want it to be infinite dimensional and stuff. And if you, I mean, you might have noticed that I didn't say anything about, or I hardly said anything about stable curves, but if we want to define this well, we should go to stable curves. And what's somewhat annoying about this is that, as I said before, so if we want to do this well, we should not give finite length to unbounded edges. So let's not do that. So my definition of a stable tropical curve and I should say that from here on out I'll be using the paper of Cavalieri, Chan, Ulrich and Weiss, a moduli stack of stable curves. So this is, yeah, I'm not going to write it out exactly, but, well, it's GRIL and H. As before, except that L of x is infinite if Rx or Rix doesn't exist. And we have some extra piece of data. I didn't write an H before. So we also have H, which is only defined from V. So from, let's say from V to N, a genus parameter. Such that, well, what's stable mean? Stable means that 2HV minus 2 plus the number of flags there, so the number of things in F, not in G, that go to V is at least, or is greater than 0. And the genus of such a curve is the sum of all these, of the genera of the vertices, plus the genus of the curve, of the graph. So B, the first better number, I guess. I should also say that, no, I should not say that yet. Definition line stack. Stable curves. So now we have two parameters. G is the total genus, and N is the number of marked points. And for some reason no one writes no bar here, but if you like it, you can put it there. It should be there, I think. Well, it's a category. With objects. So we need a monoid. FSS. And gamma stable tropical curve over M. And the morphisms should be like the morphisms in here. So what were they? Strict morphisms. And I think so. Sharp. Sorry, wrong word. Sharp. Different thing. Sharp morphisms. And we've already seen that for a morphism of monoid you get an edge contraction. So that's what we should have on the graph side. And this is clearly a moduli problem because we've basically defined it as that. We've got this part and we just add some extra data. And then the theorem of Gabalier, Jean. Schweiz. Too many names, long names. So they stated in language I haven't introduced, but anyway. So this is representable by, well, it is a geometric stack. Over the category Artin fans or rational polyhedral cones or cone complexes even if you like. And if you don't know what that is, don't bother too much about it. But I'll draw a picture, so that's kind of important. I can say in words, it's the category of, well, if you can take it to be the category of torsion-free monoids with sharp morphisms. So that's pretty nice. What does it mean to be a geometric stack? Well, you need the diagonal map to be representable by a geometric space, or a cone space in this case. In general, geometric space, I guess. And you need a surjective strict morphism from a cone complex. And I'm going to give you this in a specific example, but this will explain the general construction. And that's just a drawing. So the most important thing is exists a strict surjective morphism of some U. So MGN drop and U is a cone complex. Well, I should say Artin, I guess. And And actually this condition implies the first condition, so this is the only relevant one. And I'm just going to draw pictures now, because that's the most fun thing to do. So let's give some not completely trivial examples. I'm going to draw them over the positive real line because I can actually draw real lines, not much else. So let's start with M11. Genus 1 marked point, tropical curve. There can't be that many different ones, and that's true. Like there's only one kind of graph you can have. Well, there's two kinds, but basically got this. And in my definition of stable graph, I said that so this is a vertex. This is not a vertex. So this thing has infinite length. Hence, there's only one parameter. I guess we could call it L. Which basically means that this moduli space should be something like this. Only thing is, there are automorphisms. So I will write. So this is UG. This maps surjectively because for every element here we can give such a stable graph. But of course it's not an isomorphism because there are automorphisms. So there is also a space of relations, which I'll draw like this, where we have one thing which is the identity and one thing which is the flip. So this is, this really gives a geometric stack in the sense, geometric stack in the sense that we have a space of objects and space of morphisms, and these are the source and target maps. So it's quite explicit. Also, although of course this case is not that interesting, so I'll also give a case of M12, and then you might see a pattern, and you can generalize it. This was kind of a boring case because we only had one graph. In the case of M12, we have two graphs. Namely, we have this graph, which I'll call G1. But we also have this graph, G2. Both of them have two parameters. So we will have something like this.
The origin is like the graph which is just a vertex of genus.
Yes. So, I should probably say that. I was actually going to draw this next. Yeah. But it's a good question because I was going to draw it next, right? So I'll give some names. This edge I'll call rho. And this actually, so there are two parameters which are these two lengths in this case. And rho is the graph where one of them is 0. So this is a vertex. We also have pi, which is contracting the other one. So this now has genus 1. And actually, of course, this has genus 0, this has genus 0, but that's don't usually write. It's too much trouble. Here, it's slightly more confusing. So I'll label the edges because we can have, let's say tau E, which contracts E, which would look like this. So we still have E prime. We can also have tau E prime, which contracts E. Oh, time's by now. This is nearly up, but would like to draw the relations. So what do we have here? We now have 4 spaces of relations because we can go from this space to itself or to the other, and vice versa. So over here, we have these relations. If we're on this thing, in general, there's one automorphism, there's a flip. So as you said, probably this one I'll call the identity, but there's also a flip, F. Although if you look at this one, there's no flip, which means that they are looped along the identity of pi, and here there's an F of rho, identity of rho. You can clearly see that there are morphisms between rho and the 2 tau e's. So we've also got a component looking like this. Actually 2. So if you go from rho to tau e, I mean there's an isomorphism from rho to tau e. There are actually 2 because you can flip. And there are also 2 isomorphisms from rho to tau e prime, which means that there are 4 going from one to the other. And of course they are isomorphisms, so you can invert them letting the others. And then here, we also have the component of identities. We have a flip map here, which is a different kind of flip. So I'll call this one phi. And then we've got, so in this case we've got one automorphism phi, but if we look at these subspaces, there's a different automorphism. Like this phi is not that interesting. So phi on tau e prime goes to tau e and vice versa. But there are also automorphisms of tau e and tau e prime, just like there are morphisms from tau e to rho. So this relation space is actually like this. In the sense that, so it's not equidimensional, because if we degenerate, we get more automorphisms. But anyway, this part is U, and clearly this is a surjective map, and it's nice finite dimensional because so we need this stability for that, because otherwise we could say subdivide this edge and get an extra parameter and go on and on and on. So I think that's the end of my talk. I would have liked to say something more about how this is a universal curve, but time's up. Good.
Questions for the speaker? David.
I have questions for the authors of the paper.
Say again?
I actually have questions for the authors of the
Oh, I
paper.
should say maybe, I didn't say anything about this universal curve, but they made a mistake there. In the sense that, so they draw this in red somewhere and they forgot to draw 2 lines around it. Like 2 of these 4 should be red as well. If you actually read the paper, that could be useful. Now this is
I think I missed maybe something, but so for example, before you were just taking the y be a subdivision of the tropical curve associated to that.
Mm-hmm.
But what's a family of what's a tropical curve over S?
A subdivision of a tropical.
No, I'm saying what's the relative motion? What's a tropical curve over S?
That's something that Rosa already defined, so I thought I didn't define it anymore. But it's basically this. So you give a tropical curve over every geometric point, such that after specialization, you get, so specialization corresponds to edge contraction.
Okay, so just this condition.
Yes.
I guess generalization is edge contractions.
Oh yeah, sure. I mean, if you want to prefer covariance.
Generalization is edge contraction.
Yeah, sure. I mean,
Yeah.
the math
So you get,
it goes the other way around. Sure.